ये है द सॉलिड स्टेट। इसमें देखेंगे कि after studying this unit, we will able to describe the general characteristic of the solid state, distinguish between the amorphous and the crystalline solids, classify the crystalline solids on the basis of the nature of the binding forces, define the crystal lattice and the unit cell, explain the closed packing of the particles, describe the different types of the boards and the closed packed structures, calculate the packing efficiency of the different types of the cubic unit cells or correlate the density of a substance with its unit cell properties, or describe the imperfection in the solid and their effect in the properties, or correlate the electrical and the magnetic property of the solid and their structure. तो एनसीईआरटी कह रहा है कि फ्रॉम आवर एनसीईआरटी कह रहा है कि फ्रॉम आवर अर्लियर स्टडीज we know that liquids and the gases are called fluids because of their ability to flow. The fluidity in both of these states is due to the fact that the molecules are free to move about. On contrary, the constituent particles in the solids have fixed positions and can also oscillate about their main position. This explains the rigidity in the solids. These properties depend upon the nature of the constituent particles and the binding forces operating between them. The correlation between the structure and the property have helped in the discovery of the new solid materials with the DR property. For example, carbon nanotubes are new materials that have the potential to provide the materials that are tougher than the steel, lighter than the aluminum, and have more conductive property than the copper. Such materials may play an expanding role in the future development of the science and the society. Some other materials which are expected to play an important role in the future are high temperature superconductors, magnetic materials, biodegradable polymers for packaging, biocompliant solids for surgical implants, etc. Thus, the study of this state becomes more important in the present scenario. In this unit, we will discuss different possible arrangement of the particles resulting in the several types of the structure and explore why different arrangements of the structural units lend different properties to the solids. We also learn how these properties get modified due to the structural imperfection or by the presence of the impurities in the minute amounts. तो जनरल कैरेक्टरिस्टिक ऑफ द सॉलिड्स कुछ इस प्रकार से है कि इन द क्लास 11 you have learned that the matter can be used in the three states, namely the solid, liquid and the gas. Under given set of the condition of the temperature and the pressure, which of these would be the most stable state of a given substance depends upon the net effect of the two opposing forces. These are the intermolecular forces, which tend to keep the molecules or the atoms ions closer, and the thermal energy, which tends to keep them apart by making them move faster. At sufficiently low temperature, the thermal energy is low, and intermolecular forces bring them so close that they cling to one another and occupy the fixed position. These can still oscillate about their mean position and the substance used in the solid state. The following are the characteristic property of the solid state. पहला कि they have the definite mass, volume and the shape. दूसरा कि intermolecular distances are short. तीसरा कि intermolecular forces are strong. और चौथा कि their constituent particles, atoms, molecules or ions have the fixed position and can only oscillate about their mean position. और पांचवा है कि they are compressible and rigid. आगे है amorphous and crystalline solid. तो कहता है कि solid can be classified as the crystalline or the amorphous on the basis of the nature of the order present in the arrangement of their constituent particles. A crystalline solid usually consists of a large number of the small crystals, each of them having a definite characteristic geometrical shape. The arrangement of the constituent particles, atoms, molecules, or the ions in a crystal is ordered and repetitive in the three dimensions. If we observe the pattern in one region of the crystal, we can predict accurately the position of the particles in any other region of the crystal, however far they may be from the place of the observation. Thus, the crystal has a long range order, which means that there is a regular pattern of arrangement of the particles which repeat itself periodically over the entire crystal. Sodium chloride and the quartz are the typical examples of the crystalline solid. Glass, rubber and many plastics do not form crystals when their liquid solidify on cooling. These are called as the amorphous solid. The term amorphous comes from the Greek word amorphos, meaning no form. The arrangement of the constituent particles, atoms, molecules or ions in such solid has only short range order. In such an arrangement, a regular and periodically repeating pattern is observed over short distances only. Regular patterns are scattered in between the arrangement is disordered. The structure of the quartz crystalline and the quartz glass amorphous are shown in the figure 1.1 and A and the B respectively. While the two structures are almost identical, Yet in the case of the amorphous quartile glass, there is no long range order. The structure of the amorphous solid is similar to that of the liquid due to the difference in the arrangement of the constituent particles. The two types of the solids differ in their properties. अच्छा, यहाँ पर अब दिया हुआ है कि द टू डायमेंशनल स्ट्रक्चर ऑफ द क्वार्टेज एंड द क्वार्टेज ग्लास दिया हुआ है। क्वार्टेज जो है वो है क्रिस्टलाइन सॉलिड, ठीक है, लेकिन क्वार्टेज ग्लास जो होता है वो होता है अमोर्फस सॉलिड। आगे एनसीईआरटी कह रहा है कि crystalline solid have a sharp melting point at a characteristic temperature. They melt abruptly and become liquid. On the other hand, amorphous solid of soften, melt and start flowing over a range of the temperature and can be molded and blown into the various shapes. Amorphous solids have the same structural feature as liquids and are conventionally regarded as extremely viscous liquid. They may become crystalline at the some temperature. Some glassy objects from the ancient civilization are found to be become milky in appearance because of this some crystallization. Like the liquids, amorphous solids have a tendency to flow, though very slowly. Therefore, sometimes these are also called as the pseudo solids or the supercooled liquids. Amorphous solids are isotropic in the nature. Their properties such as the mechanical strength, refractive index, and electrical conductivity, etc., are same in all directions. It is because there is no long-range order in them, and arrangement of the particles is not definite along all the directions. Hence, the overall arrangement becomes equivalent in all the directions. Therefore, the value of any physical property would be become same along any direction. नेक्स्ट है कि crystalline solids are anisotropic in the nature. That is some of their physical property like the electrical resistance or the refractive index for different values when measured along different direction in the same crystal. This arises from the different arrangement of the particles in the different direction. This is illustrated in the figure 1.2. This figure shows a simple two-dimensional pattern of the arrangement of the two kinds of the atoms. Mechanical properties such as the resistance to the sharing of stress might be quite different in the two directions indicated in the figure. Deformation in the CD direction displaces row which have two different types of the atoms, while in the AB direction row is made of one type of the atoms are displaced. The difference between the crystalline solids and the amorphous solids are summarized in the table 1.1. अब यहाँ पर दिया हुआ anisotropy in the crystal is due to the different arrangement of the particle along the different direction. तो डिस्टिंक्शन बिटवीन द क्रिस्टलाइन एंड अमorphous सॉलिड दिए हुए एनसीईआरटी क्रिस्टलाइन सॉलिड्स के बारे में कहता है कि क्रिस्टलाइन सॉलिड्स ऑफ द डिफरेंट कैरेक्टरिस्टिक ज्योमेट्रिकल शेप और मेल्ट एट द शार्प एंड कैरेक्टरिस्टिक टेम्परेचर पर। क्लीवेज प्रॉपर्टी है कि when cut with a sharp edge tool they split into two pieces and the newly generated surface are plain and smooth. हीट ऑफ फ्यूजन के बारे में क्रिस्टलाइन सॉलिड्स का है कि दे हैव ए डेफिनेट एंड कैरेक्टरिस्टिक इंथैल्पी ऑफ फ्यूजन और एनिसोट्रॉपिक इन नेचर होता है। ये ट्रू सॉलिड्स हैं और लॉन्ग रेंज ऑर्डर होता है, जबकि अमॉर्फस सॉलिड इरेगुलर शेप के होते हैं, gradually soften over a long range of the temperature, or when cut with a sharp edge tool they cut into two pieces with the irregular surfaces, or they do not have the definite enthalpy of the fusion. आगे है कि जो अमॉर्फस सॉलिड होता है वो आइसोट्रॉपिक in नेचर होता है और इसे सूडो सॉलिड्स और सुपर कूल्ड लिक्विड भी कहते हैं, और इसमें है जो शॉर्ट रेंज ऑर्डर ही सिर्फ है जो होते हैं। आगे एनसीईआरटी लिख रहा है कि besides the crystalline and the amorphous solids, there are some solids which apparently appear amorphous but have microcrystalline structure. These are called as the polycrystalline solids. Metal often occur in the polycrystalline condition. Individual crystals are randomly oriented, so a metallic sample may appear to be isotropic even though a single crystal is anisotropic. Amorphous solids are useful in materials, glass, rubber, and the plastics. Find many applications in our daily life. Amorphous silicon is one of the best photovoltaic materials available for the conversion of sunlight into the electricity. अब है क्लासिफिकेशन ऑफ द क्रिस्टलाइन सॉलिड्स। तो एनसीईआरटी कहता है कि इन द सेक्शन 1.2 वी हैव लर्नड अबाउट द अमॉर्फस सब्सटेंस एंड दैट दे ओनली हैव शॉर्ट रेंज ऑर्डर. However, most of the solid substances are crystalline in the nature. For example, all the metallic elements like the iron, copper, and silver, non-metallic elements like the sulfur, phosphorus, and iodine, and compounds like the sodium chloride, zinc sulfide, and naphthalene form the crystalline solid. Crystalline solids can be classified in the various ways. The method depends on the purpose in the hand. Here we will classify the crystalline solids on the basis of the nature of the intermolecular forces or the bonds that hold the constituent particles together. These are the van der Waals forces, ionic bonds, covalent bonds, and the metallic bonds. On the basis of the crystalline solids are classified into four categories, namely molecular, ionic, metallic, and the covalent solids. Let us learn about these categories. तो molecular solids क्या होते हैं? तो molecules are the constituent particles of the molecular solids. These are further subdivided into following subcategories. Non-polar molecular solids, so they are comprised either atoms, for example argon and helium, or the molecules formed by the non-polar covalent bonds, for example H2Cl2 and the I2. In these solids, the atoms or the molecules are held by the big dispersion forces or the London forces, about which you have learnt in the class 11. These solids are soft and non-conductors of the electricity. They have low melting point and are usually in the liquid or the gaseous state at the room temperature and the pressure. फिर आता है सेकंड है पोलर मॉलिकुलर सॉलिड्स, तो कहता है कि द मॉलिक्यूल्स ऑफ द सब्सटेंसेस लाइक द HCl, SO2 etc. are formed by the polar covalent bonds. The molecules in such solids are held together by the relative stronger dipole-dipole interaction. These solids are soft and non-conductors of the electricity. Their melting points are higher than those of the non-polar molecule solids, yet most of these are gases or the liquid under the room temperature and pressure. Solid SO2 and the solid Na3 are some examples of such solids. और तीसरा है हाइड्रोजन बॉन्डेड मॉलिक्यूलर सॉलिड्स. द मॉलिक्यूल ऑफ सच सॉलिड्स कंटेन द पोलर कोवेलेंट बॉन्ड्स बिटवीन द H and the phone atoms. Strong hydrogen bonding binds molecules of such solids like the H2O ice. They are non-conducting of the electricity. Generally, they are volatile liquids or soft solid under the room temperature and the pressure. Ionic solids की बात करें तो ions are the constituent particles of the ionic solids. Such solids are formed by the three-dimensional arrangement of the cations and anions bound by the strong Coulombic electrostatic forces. These solids are hard and brittle in the nature. They have high melting and the boiling point. Since the ions are not free to move about, they are electrical insulator in the solid state. However, in the molten state or when dissolved in the water, the ions become free to move about and they conduct the electricity. Metallic solids क्या होते हैं? तो metals are orderly collection of the solid positive ions surrounded by and held together by a sea of the free electrons. These electrons are mobile and are evenly spread out throughout the crystal. Each metal atom contributes one or more electrons towards this sea of the mobile electrons. These free and the mobile electrons are responsible for the high electrical and thermal conductivity of the metals. When an electrical field is applied, these electrons flow through the network of the positive ions. Similarly, when heat is applied to one portion of a metal, the thermal energy is uniformly spread throughout by the free electrons. Another important characteristic of the metal is their luster and the color in the certain cases. This is also due to the presence of the free electrons in them. Metals are highly malleable and ductile. आगे है कोवेलेंट और द नेटवर्क सॉलिड, तो कहता है कि वाइड वेराइटी ऑफ द क्रिस्टलाइन सॉलिड of the non-metals results from the formation of the covalent bonds between the adjacent atoms throughout the crystal. They are also called the giant molecules. Covalent bonds are strong and directional in the nature, therefore atoms are held very strongly at their position. Such solids are very hard and brittle. They have extremely high melting points and may even decompose before melting. They are insulated and do not conduct electricity. जैसे diamond and silicon carbide are typical examples of such solids. Although graphite also belong to this class, कहता है कि all graphite also belong to this class of the crystal, but it is soft and the conductor of the electricity. Its exceptional properties are due to its typical structure. Carbon atoms are arranged in different layers and each bond is covalently bonded to three of its neighboring atoms in the same layer. The fourth valence electron of each atom is present between the different layers and is free to move about. These free electrons make the graphite a good conductor of the electricity. Different layers can slide over one another. This makes the graphite a soft, solid and a good solid lubricant. The different properties of the four type of the solids are listed in a table 1.2 में दिए हुए. उससे पहले कि ये हो गया नेटवर्क स्ट्रक्चर ऑफ द डायमंड, जिसमें जो कि दो एटम के बीच में 154 पिकोमीटर का आता है और ग्रेफाइट में दो लेयर के बीच में 340 पिकोमीटर का डिस्टेंस आता है और दो एटम के बीच में 141.5 पिकोमीटर का डिस्टेंस आता है. तो ये स्ट्रक्चर ऑफ दी ग्रेफाइट दिए हुए. अब डिफरेंट टाइप्स ऑफ सॉलिड की बात करें तो मॉलिकुलर सॉलिड्स में आता है नॉन पोलर, जिसमें कॉन्स्टेंट है मॉलिक्यूल्स. पोलर में भी कॉन्स्टेंट मॉलिक्यूल्स, हाइड्रोजन में भी बॉन्डेड में भी मॉलिक्यूल्स ही कॉन्स्टेंट आएंगे. नॉन पोलर में डिस्पर्सन और लंदन फोर्स हो जाता है. इसका एग्जाम्पल हो गया AR ठीक है। Cl4H2I2CO2 सॉफ्ट हो जाते हैं, इंसुलेटर होता है और मेल्टिंग पॉइंट इसका वेरी लो होता है। पोलर में डायपोल डायपोल इंटरेक्शन होता है, HCl आता है, H2 आता है, ये सॉफ्ट होता है, इंसुलेटर होता है और मेल्टिंग पॉइंट लो होता है। हाइड्रोजन बॉन्डेड में H2O आइस होता है, फिजिकल नेचर इसका हार्ड होता है, ये इंसुलेटर होता है और मेल्टिंग पॉइंट इसका लो हो जाता है। आयोनिक सॉलिड्स में आयन्स हो जाते हैं, कोलम्बिक और इलेक्ट्रोस्टैटिक फोर्स आता है इसमें। NaCl, MgO, ZnF और CF2 आता है, हार्ड बट ब्रिटल होते हैं। इंसुलेटर इन द सॉलिड स्टेट बट कंडक्टर्स इन द मोल्टन स्टेट एंड इन द सॉल्यूशन होता है और मेल्टिंग पॉइंट इसका हो जाता है हाई। मेटलिक सॉलिड्स की बात करें तो पॉजिटिव आयन्स इन द सी ऑफ द डिलोकुलाइड इलेक्ट्रॉन्स होता है, मेटलिक बॉन्डिंग इसमें होता है और FeCu, Ag और Mg आता है, हार्ड बट मेलेबल एंड डक्टाइल होता है और कंडक्टर्स इन द सॉलिड स्टेट एज वेल एज इन द मोल्टन स्टेट होता है और फेयरली हाई इसका हो जाता है मेल्टिंग पॉइंट। फिर कोवलेंट और नेटवर्क सॉलिड्स की बात करें तो एटम्स इसमें आ गए कॉन्स्टेंट पार्टिकल्स। कोवलेंट बॉन्डिंग होता है इसमें FiO2 क्वार्टेज, FiC डायमंड और AlN और ग्रेफाइट आ जाता है कोवलेंट और नेटवर्क सॉलिड में। इसमें जो FiO2, FiC और डायमंड जो होता है हार्ड होता है, लेकिन एल्युमिनियम नाइट्राइड और ग्रेफाइट है जो सॉफ्ट हो जाते हैं। FiO2, FiC और कार्बन जो है इंसुलेटर है और इसका मेल्टिंग पॉइंट बहुत हाई होता है, लेकिन जो ग्रेफाइट है वो कंडक्टर है और ये एक्सेप्शन में आ जाता है। अब देखेंगे क्रिस्टल लैटिस एंड द यूनिट सेल्स। तो Ncert कहता है कि you must have noticed that when the tiles are placed to cover a floor, a repeated pattern is generated. If they are, after sending tiles on the floor, we mark a point at the same location in all the tiles, center of the tile, and see the marked position only ignoring the tiles, we obtain a set of the points. This set of the points with the scaffolding on which the pattern has been developed by placing tile. This scaffolding is a space lattice on which the two-dimensional pattern has been developed by placing the structural unit on its sets of the point. That means tile in the case. The structural unit is called the basis on or the motif. When the motifs are placed on the points in the space lattice, a pattern is generated. In the crystal structure, motif is a molecule, atom or the ion. A space lattice, also called a crystal lattice, is the pattern of the point representing the location of these motifs. In other words, a space lattice is an abstract scaffolding for the crystal structure. When we place motifs in the identical manner on play point of the space lattice, so we get the crystal structure. Figure 1.5 shows a motif, a two-dimensional lattice and a hypothetical two-dimensional crystal structure obtained by placing motifs in the two-dimensional lattice. A special arrangement of the lattice point gives rise to different types of the lattice. Figure 1.6 shows the arrangement of the points in the two different lattices. ये lattice A हो गया और ये हो गया lattice B. तो अरेंजमेंट ऑफ द पॉइंट्स इन टू डिफरेंट लैटिस से दिखाया हुआ है। इन द केस ऑफ द क्रिस्टलाइन सॉलिड स्पेस लैटिस इज ए थ्री डायमेंशनल अरे ऑफ द पॉइंट्स। द क्रिस्टल स्ट्रक्चर इज ऑब्टेन्ड बाय एसोसिएटिंग structural motifs with the lattice point. Each repeated basis or the motif has the same structure and same spatial orientation as the other one in a crystal. The environment of each motif is same throughout the crystal except for on the surface. और following are the characteristic of a crystal lattice. पहला कि each point in a lattice is called a lattice point or the lattice site. दूसरा कि each point in a crystal lattice represents one constant particles which may be an atom, a molecule or a group of the atom or an anion. Lattice points are joined by straight lines to bring out the geometry of the lattice. Or we need only a small part of the space lattice of a crystal to specify the crystal completely. This small part is called a unit cell. One can choose the unit cell in many ways. Normally that cell is chosen which has perpendicular sides of the shortest length, and one can construct entire crystal by the transitional displacement of the unit cell in the three dimension. Figure 1.1 shows the movement of the unit cell of a two-dimensional lattice to construct the entire crystal structure. Also, unit cell have the shapes Also, units will have the shapes that they fill the whole lattice without leaving the space between the cells. In the two dimension, a parallelogram with the side of the length A and B and the angle R obtained between these sides is chosen as the unit cell. Possible unit cell in the dimension are shown in the figure 1.8. तो यहाँ पर दिखाया हुआ है generating the hypothetical two-dimensional crystal structure by shifting the square in the direction of the arrows. और यहाँ पर दिखाया हुआ है इस तरफ ये सब मोटिफ हो गया स्पेस लैटिस टू डायमेंशनल हाइपोथेटिकल टू डायमेंशनल क्रिस्टल स्ट्रक्चर है जो हो गया है। अब है पॉस्फेल यूनिट सेल्स। तो पॉस्फेल यूनिट सेल कुछ इस प्रकार से हो सकते हैं, ठीक है। तो यहाँ पर दिखाए हुए a portion of a 3-dimensional cubic space of a crystal lattice and its unit cell। तो आगे एनसीईआरटी कहता है कि पोर्शन ऑफ द 3-dimensional crystal lattice and its unit cell is shown in the figure 1.9। In the 3-dimensional crystal, the structure unit cell is characterized by its dimension along the 3 edges A, B, and C. These edges may or may not be mutual perpendicular. Angle between the edges A between the B and C, beta between the A and C, and gamma between A and B. Thus, a unit cell is characterized by the fixed parameter A, B, C, alpha, beta, or gamma. These parameters of a typical unit cell are shown in the figure 1.0। और अब आता है प्रिमिटिव एंड द सेंटर्ड यूनिट सेल। तो यूनिट सेल कैन यू ब्रॉडली कहता है कि यूनिट सेल, ठीक है। आगे कहता है एनसीईआरटी कि यूनिट सेल कैन यू ब्रॉडली डिवाइडेड इनटू 2 कैटेगरीज, प्रिमिटिव एंड द सेंटर्ड यूनिट सेल। प्रिमिटिव यूनिट सेल के बारे में कह रहा है कि व्हेन द कांस्टेंट पार्टिकल्स आर प्रेजेंट ओनली ऑन द कॉर्नर पोजीशन ऑफ ए यूनिट सेल, इट इज कॉल्ड एज द प्रिमिटिव यूनिट सेल। और सेंटर्ड यूनिट सेल होता है कि व्हेन ए यूनिट सेल contains one or more constant particles present at the position other than the corners in addition to those at the corners, it is called a centered unit cell। centered unit cell are of two types, और centered unit cell are of three types। पहला body centered unit cell, such a unit cell contains one constant particles, atoms, molecule or ions at its body center besides the one that are its corners। दूसरा फेस सेंटर्ड यूनिट सेल, तो सच यूनिट सेल contains one constant particles present at the center of the each face besides the one that are at its corner। और तीसरा है इन सेंटर्ड यूनिट सेल। तो इन सच ए यूनिट सेल वन constant particles is present at the center of any two opposite faces besides the one present at its corner पर। आगे बढ़ जाते हैं। तो आगे कहता है कि इंस्पेक्शन ऑफ ए वाइड वैरायटी ऑफ द क्रिस्टल लीड टू द कंक्लूजन दैट ऑल कैन बी रिगार्डेड एज ए कन्फॉर्मिंग टू वन ऑफ द 7 रेगुलर फिगर्स। दिस बेसिक regular figures are called the 7 crystal system। To which crystal system a given crystal belong to is determined by measuring the angles between its faces and deciding how many axes are needed to define the principal feature of its shape। फिगर 1.11 for the 7 crystal system, ठीक है। ये हो गया क्यूबिक, फिर आता है टेट्रागोनल, ऑर्थोरोम्बिक, हेक्सागोनल, रोम्बोहेड्रल, मोनोक्लिनिक और ट्राइक्लिनिक। तो 7 क्रिस्टल सिस्टम से जो दिए हुए हैं। A French mathematician Bravais showed that there are only 14 possible 3-dimensional lattices। These are called as the Bravais lattices। Unit cells of these lattices are shown in the following box। The characteristic of the primitive unit cell along with the centered unit cell that they can form will listed in table 1.1। तो इस टेबल को ऐसे देख सकते हैं, क्रिट होमेट से है जो देख सकते हैं। कुछ CFD है जैसे कि क्रिट होमेट, ठीक है। क्रिट होमेट आ जाता है, CFD हो गया ये क्रिट होमेट। C से क्यूबिक, R से रोम्बोहेड्रल, T से हो जाता है ट्राइगोनल, H से हो जाता है, H से हेक्सागोनल, O से ऑर्थोरोम्बिक, M से मोनोक्लिनिक और T से ट्राइक्लिनिक, ठीक है। इसके बाद फिर आता है कि पहले 2 के लिए लेंथ इक्वल, बाद के लिए 2 इक्वल, और लास्ट के जो 3 है उसके लिए तीनों लेंथ अनइक्वल। एंगल की बात करें तो अल्टरनेटिवली एंगल की बात करें तो कुछ इस प्रकार से है कि अल्टरनेटिवली यानी कि इसमें और इसमें जो होगा अल्फ़ा बीटा गामा इक्वल टू 90 डिग्री हो जाएगा, ठीक है। अल्टरनेटिवली चल रहे हैं तो ऑर्थोरोमिक में भी आना चाहिए, ऑर्थोरोमिक में भी अल्फ़ा बीटा गामा इक्वल टू आ जाएगा 90 डिग्री। तो अल्टरनेटिवली अल्फ़ा बीटा गामा इक्वल टू अल्टरनेटिवली पहले अल्फ़ा बीटा गामा इक्वल टू 90 डिग्री, फिर रोम्बोहेड्रल में आ जाएगा कितना, फिर उसके बाद फिर आता है अल्फ़ा इक्वल टू बीटा गामा इज नॉट इक्वल टू 90, ठीक है। इसमें फिर आ जाएगा अल्फ़ा इक्वल टू बीटा इक्वल टू 90 और गामा इक्वल टू 120, और फिर मोनोक्लिनिक में आ जाएगा अल्फ़ा इक्वल टू गामा इक्वल टू 90 और बीटा इज नॉट इक्वल टू 90, और फिर ट्राइक्लिनिक में तीनों ही आपस में इक्वल नहीं है और नॉट इक्वल टू 90 है। सही हो गया। उसके बाद फिर आता है 312 1421 का रूल। इसके बाद फिर है 312 1421 और PBFE। बस एक एक्सेप्शन है कि मोनोक्लिनिक में क्या होता है कि P होता है और E आता है, यानी कि प्रिमिटिव होता है और इनसेंटर्ड आता है। बाकी पॉसिबल वेरिएशन एक्चुअल डिस्टेंस और एक्चुअल एंगल हो गया। अब एग्जाम्पल की बात करते हैं। तो एग्जाम्पल क्यूबिक में आता है NaCl, जिंक प्लेंट और Cu, ठीक है, कॉपर। फिर देखते हैं रोम्बो टेट्रागोनल में। तो टेट्रागोनल में आता है भाइट टिन, ठीक है। टेट्रागोनल में क्या क्या आता है? तो टेट्रागोनल में आता है भाइट टिन, FnO2, TiO2 और CSO4। ऑर्थोरोमिक में एग्जाम्पल है रोमिक सल्फर, KNO3 और BSO4। हेक्सागोनल में है ग्रेफाइट, ZnO और CDF। रोम्बोहेड्रल और ट्रायगोनल में आता है कैल्साइट, CaCO3, HgS, सिन्नाबार यानी। और मोनोक्लोनिक का एग्जाम्पल आता है मोनोक्लोनिक सल्फर, ठीक है, और Na2SO4, 10H2O। ट्राइक्लिनिक में आता है K2Cr2O7, CuSO4, 5H2O और H3BO3, ऑर्थोबोरिक एसिड आ जाता है ट्राइक्लिनिक में, ठीक है। ये टेबल कंप्लीट हो गया। एग्जाम्पल से शायद नहीं आता है क्वेश्चन। अब यहाँ पर दिया हुआ है यूनिट सेल ऑफ द 14 टाइप्स ऑफ द ब्रेविस लैटिसेज। तो सबसे पहले है यूनिट सेल ऑफ द क्यूबिक लैटिसेज इन ऑल साइड ऑफ द सेम लेंथ, एंगल्स बिटवीन द ऑल फेसेज 90 डिग्री। तो इसमें प्रिमिटिव आता है, बॉडी सेंटर्ड है और फेस सेंटर्ड है, ठीक है। आगे में है कि यूनिट सेल ऑफ द टेट्रागोनल लैटिस, वन साइड डिफरेंस इन द लेंथ ऑफ द अदर, टू एंगल्स बिटवीन द फेसेज ऑल 90 डिग्री। तो टेट्रागोनल में प्रिमिटिव आता है और बॉडी सेंटर्ड आता है। नेक्स्ट दिए हुए है कि यूनिट सेल्स ऑफ द 4 ऑर्थोरोमिक लैटिस, अनइक्वल साइड्स, एंगल बिटवीन ऑल फेसेज ऑल 90। तो इसमें आता है प्रिमिटिव, इन सेंटर्ड, बॉडी सेंटर्ड और फेस सेंटर्ड। नेक्स्ट है यूनिट सेल्स ऑफ द 2 मोनोक्लिनिक लैटिसेज, अनइक्वल साइड्स, टू फेसेज हैविंग द एंगल डिफरेंट टू द 90। तो इसमें प्रिमिटिव आता है और इन सेंटर्ड है जो आएगा। अब यहाँ पर दिए हुए हैं कि यूनिट सेल ऑफ द हेक्सागोनल लैटिस, वन साइड डिफरेंट टू द लेंथ ऑफ द अदर, मार्केट बिटवीन द टू फेसेज ऑफ द 60 डिग्री। और यहाँ पर दिया यूनिट सेल ऑफ द रोम्बोहेड्रल लैटिस, ऑल साइड्स ऑफ द इक्वल लेंथ, साइड्स ऑन द टू फेसेज आर लेस देन 90 डिग्री। इधर है यूनिट सेल ऑफ द ट्राइक्लिनिक लैटिस, अनइक्वल साइड ABC आर अनइक्वल, एंगल विथ नॉन अनइक्वल टू द 90 डिग्री। अब बात करते हैं नंबर ऑफ द एटम्स इन द यूनिट सेल में। तो Ncert कहता है कि we know that any crystal lattice is made up of a very large number of the unit cell and every lattice point is occupied by one constant particles, atom, molecule or the ion. Let us now work out what proportion of the each particle belong to a particular unit cell. तो कहता है we shall consider 3 types of the cubic unit cell and for the simplicity assume that the constant particle is an atom. तो primitive cubic unit cell, तो कहता है primitive cubic unit cell है the one atom only at its corner. Each atom at a corner is shared between the 8 adjacent unit cell as shown in the figure 1.12. 4 unit cell in the same layer and the 4 unit cell of the upper or lower layer. Therefore, only 1/8 of an atom or the molecule or ion actually belong to a particular unit cell. In figure 1.13, a primitive cubic unit cell has been depicted in the 3 different ways. Each small sphere in the figure 1.13A1 represents only the center of the particles occupying that position and not its actual size. Such structures are called as the open structure. The arrangement of the particles is easier to follow in the open structure. Figure 1.3b depicts the space filling representation of the unit cell with the actual particle size, and figure 1.13c for the actual portion of the different atoms present in a cubic unit cell. In all, since each cubic unit cell has 8 atoms on its corner, the total number of the atoms in the one unit cell 8 into 8 यानी कि 1 atom आ जाएगा. The primitive cubic unit cell has the open structure, space filling structure, actual proportion of the atoms belonging to the one unit cell. अब इधर दिए हुए in a simple cubic unit cell, each corner atom is shared between the 8 unit cells है जो हो जाता है. अब बात करते हैं बॉडी सेंटर्ड क्यूबिक यूनिट सेल. तो बॉडी सेंटर्ड में अ बॉडी सेंटर्ड क्यूबिक यूनिट सेल BCC यूनिट हैज एन एटम एट ईच ऑफ इट्स कॉर्नर and also one atom at its body center. Figure 1.14 depicts open structure of space filling model and the unit cell with the portion of the atom actually belonging to it. It can be seen that the atom at the body center wholly belong to the unit cell in which it is present. Thus, in a body center cubic BCC unit cell, 8 corners into 1/8 per corner atom आ जाएगा 8 into 1/8 यानी कि 1 atom, और एक बॉडी सेंटर एटम इक्वल टू 1 1 1 यानी कि 1 एटम आ जाएगा. तो टोटल नंबर ऑफ एटम्स पर यूनिट सेल आ जाएगा 2 एटम्स. आगे बढ़ जाते हैं. तो आगे है कि फेस सेंटर्ड क्यूबिक यूनिट सेल. तो फेस सेंटर्ड क्यूबिक यूनिट सेल FCC यूनिट सेल contains almost at atoms all the corners and at the centers of all the faces of the cube. It can be seen in the figure 1.15 that each atom located at the face center is shared between the 2 adjacent unit cell and only half of each atom belong to a unit cell. Figure 1.16 depicts open structure of space filling model and the unit cell with portion of the atoms actually belong to it. Thus in a face center cubic axis unit cell 8 कॉर्नर एटम गुना 1/8 तो आ जाएगा 1 एटम, और 6 फेस सेंटर रहता है तो उसका कंट्रीब्यूशन होता है हाफ, तो आ जाएगा 3 एटम्स। तो टोटल नंबर ऑफ एटम्स पर यूनिट सेल आ जाएगा कितना, 4। आगे बढ़ते हैं तो कहता है कि फेस सेंटर्ड क्यूबिक यूनिट सेल ओपन स्ट्रक्चर स्पेस फिलिंग स्ट्रक्चर एक्चुअल पोर्शन ऑफ द सम एटम्स बिलोंग टू द वन यूनिट सेल है, जो दिया हुआ है, ठीक है। और यहाँ पर एन एटम एट द फेस सेंटर ऑफ द यूनिट सेल इज शेयर्ड बिटवीन द 2 यूनिट सेल। अब एनसीईआरटी क्लोज पैक्ड स्ट्रक्चर के बारे में कर रहा है कि इन सॉलिड्स द कांस्टेंट पार्टिकल्स आर क्लोज पैक्ड leaving the minimum vacant space. Let us consider the constituent particles as identical hard spheres and build up of the three-dimensional structure in the three step. तो पहला है क्लोज पैकिंग इन द वन डायमेंशन। तो कहता है कि देयर ओनली वन वे ऑफ द अरेंजिंग स्क्वायर्स इन अ वन डायमेंशनल क्लोज पैक्ड स्ट्रक्चर, दैट इज टू अरेंज देम इन अ रो एंड टचिंग ईच अदर। In this arrangement, each sphere is in contact with the two of its neighbor. The number of the nearest neighbors of a particle is called its coordination number. Thus, in one-dimensional closed packed arrangement, the coordination number is 2. B है closed packing in the two dimension। तो कहता है कि two-dimensional closed packed structure can be generated by stacking या placing the rows of the closed packed sphere. This can be done in the two different ways. पहला कि the second row may be placed in contact with the first one, such that the sphere of the second row are exactly above those of the first row. The sphere of the two rows are aligned horizontally as well as vertically. If we call the first row as the A-type row, the second row exactly the same as the first one is also of the A-type. Similarly, we may place more rows to obtain a type of the arrangement as shown in the figure 1.18a. तो ए में दिया हुआ है स्क्वायर क्लोज पैकिंग और बी में दिया हुआ है हेक्सागोनल क्लोज पैकिंग ऑफ द स्क्वायर इन द टू डायमेंशंस। और यहाँ पर दिखाए हुए है क्लोज पैकिंग ऑफ द स्क्वायर्स इन द वन डायमेंशंस में। अब आगे एनसीईआरटी कहता है कि इन दिस अरेंजमेंट ईच स्क्वायर इज इन कॉन्टैक्ट विद द फोर ऑफ इट्स नेबर, thus the two-dimensional coordination is 4. Also, if the centers of these four immediate neighboring spheres are joined, a square is formed. Hence, this packing is also called the square closed packing in the two dimension. Next, the second row may be placed above the first one in a staggered manner, such that its spheres fit in the depression of the first row. If the arrangement of the sphere in the first row is called the A type, the one in the second row is different and may be called the B type. When the third row is placed adjacent to the second in the staggered manner, its spheres are aligned with those of the first layer, hence this layer is also of the A type. The sphere of the similarly placed fourth row will be aligned with those of the second row P type, hence this arrangement is of the AB type. In this arrangement, there is a less free space and this packing is more efficient than the square closed packing. Each sphere is in contact with the six of its neighbors and the two-dimensional coordination number is 6. The center of these six spheres are at the corners of a regular hexagon. Hence, this packing is called as the two-dimensional hexagonal closed packing. It can be seen in the figure 1.18b that in this layer there are some voids, empty spaces. These are triangular in the shape. The triangular voids are of two different types. In one row, the apex of the triangles are pointing upwards, and in the next layer, downwards. क्लोज पैकिंग इन द थ्री डायमेंशन देखें तो ऑल रियल स्ट्रक्चर आर थ्री डायमेंशनल स्ट्रक्चर, दे कैन बी ऑब्टेन्ड बाय स्टैकिंग टू डायमेंशनल लेयर्स वन above the other. In the last section we discussed closed packing in the two dimensions which can be two types of square closed packed and the hexagonal closed packed. Let us see what type of three dimensional closed packing can be obtained from these. So three dimensional closed packing forms two dimensional square closed packed layers. While placing the second square closed packed layer above the first, we follow the same rule that was followed when one row was placed adjacent to the other. The second layer is placed over the first layer such that the sphere of the upper layer are exactly above those of the first layer. In this arrangement, the sphere of both the layers are perfectly aligned horizontally as well as vertically as shown in the figure 1.19. Similarly, we may place more layers on one above the other. If the arrangement of the sphere edge of the first layer is called A type, all the layers have the same arrangement. Thus, this lattice is the AAA type pattern. This lattice is the unity of the simple cubic lattice and its unit cell is the primitive cubic unit cell. Next है three-dimensional closed packing from the two-dimensional hexagonal closed packed layers. Three-dimensional closed packed structure can be generated by placing layers one above the other. और यहाँ पर ये दिए हुए सिंपल क्यूबिक लैटिस फॉर्मड बाय द ए अरेंजमेंट और प्लेसिंग द सेकंड लेयर ओवर द फर्स्ट लेयर. तो कहता है कि लेट अस टेक ए टू डायमेंशनल हेक्सागोनल क्लोज पैक्ड लेयर ए and place a similar layer above it such that the spheres of the second layer are placed in the depression of the first layer. Since the sphere of the two layers are aligned differently, let us call the second layer as the B. It can be observed from the figure 1.20 that all the triangular parts of the first layer are not covered by the sphere of the second layer. This gives rise to the different arrangements. Whenever a sphere of the second layer is above the void of the first layer of the vice versa, a tetrahedral void is formed. These voids are called the tetrahedral voids because a tetrahedron is formed when the centers of these four spheres are joined. They have been marked as a T in the figure 1.20. One such void has been shown separately in the figure 1.21. तो यहाँ पर स्टैक ऑफ द टू लेयर्स ऑफ द क्लोज पैक्ड स्फीयर्स एंड द voids जनरेटेड इन देम. टी जो है टेट्राहेड्रल void है और ओ जो है ऑक्टाहेड्रल void को दिखा रहा है. तो टेट्राहेड्रल एंड द ऑक्टाहेड्रल voids टॉप व्यू दिया हुआ है ए में, बी में दिया हुआ है एक्सप्लोडेड व्यू साइड एंड 3C में दिया हुआ है ज्योमेट्रिकल शेप ऑफ द void. तो ये अगर 3 नीचे और 3 ऊपर है तो ऑक्टाहेड्रल होल हो जाएगा. अगर 3 नीचे 1 ऊपर है तो टेट्राहेड्रल होल. ठीक है, इस तरफ से टेट्राहेड्रल होल हो गया, यहाँ पर ये ऑक्टाहेड्रल हो गया. टेट्राहेड्रॉन को इस तरफ दिखा सकते हैं, ऑक्टाहेड्रॉन को है जो इस तरफ से दिखा सकते हैं. नेक्स्ट एनसीईआरटी कहता है कि एट अदर प्लेसेस द ट्रायंगुलर voids इन द सेकंड लेयर आर अबव द ट्रायंगुलर voids इन द फर्स्ट लेयर एंड द ट्रायंगुलर शेप्स ऑफ दीज डू नॉट ओवरलैप. One of them by the apex of the triangular pointing upwards and the other downwards. These voids have been marked as O in the figure 1.20. Such voids are surrounded by the six spheres and are called as the octahedral voids. One such void has been shown separately in the figure 1.21. The number of these two types of the voids depend upon the number of the closed packed sphere. To let the number of the closed packed sphere be n, then the number of the octahedral voids generated बराबर आ जाएगा n. And the number of the tetrahedral void generated आ जाएगा 2n. Placing third layer over the second layer, तो कहता है कि when the third layer is placed over the second layer, there are two possibilities. पहला, covering the tetrahedral voids. The tetrahedral void of the second layer may be covered by the sphere of the third layer. In this case, the sphere of the third layer are exactly aligned with those of the first layer. Thus, the pattern of the sphere is repeated in the alternate layers. This pattern is often written as the ABAB pattern. This structure is called the hexagonal closed packed HCP structure. This sort of the arrangement of the atoms is found in many metals like the magnesium and zinc. तो HCP मैग्नीशियम और जिंक में है जो मिलता है. यहाँ पर दिए हुए हेक्सागोनल क्यूबिक क्लोज पैक्ड एक्सप्लोडेड व्यू showing the stacking of the layers of the sphere. और बी में है 4 layers stacked in each case and geometry of the packing है जो दिखाया हुआ है. यहाँ पर दिखाया हुआ है ए बी सी. तो ए बी सी जो होता है वो एफ में होता है, अरेंजमेंट ऑफ द लेयर्स व्हेन द ऑक्टाहेड्रल void इज कवर्ड. और एच में होता है ए बी अरेंजमेंट. सही है. तो एच में कैसा होगा, एच में हो जाता है ए बी. ठीक है, एच में होता है ए बी और ए बी सी किस हो जाता है एफ में. सी किस में आता है एफ में. तो ए बी सी किस में आएगा एफ में. इस तरह से एफ में है सी तो इसमें आ जाएगा ए बी सी. क्लियर हो गई बात. Octahedral fragments of the structure formed by this arrangement resulting in the cubic closed packed CCP or the face centered structure FCC. तो FCC को ही क्या कहते हैं, FC को ही कहते हैं CCP भी कहते हैं. अगेन यहाँ C है तो ABC. इस तरह से बनता है हेक्सागोनल पैकिंग और इस तरह से बनता है क्यूबिक क्लोज पैकिंग. अब आगे एनसीईआरटी बोलता है कवरिंग द ऑक्टाहेड्रल voids. तो कहता है कि द थर्ड लेयर में बी प्लेस्ड above द सेकंड लेयर इन अ मैनर सच दैट इट स्फीयर्स कवर द ऑक्टाहेड्रल voids. When placed in this manner, the sphere of the third layer are not aligned with those of either the first or the second layer. This arrangement is called the C type. Only when fourth layer is placed, its spheres are aligned with those of the first layer as shown in the figure 1.22 and the 1.23. This pattern of the layer is often written as the ABC. This structure is called the cubic closed packed CCP or the face-centered FCC structure. Metals such as the copper and the silver crystallize in this structure. Both the type of the closed packing are highly efficient and 24% of space in the crystal lattice is filled. In either of them, each sphere is in contact with the 12th sphere, thus the coordination number is 12 in either of these two structures. अब होता है formula of a compound and a number of the voids. तो एनसीईआरटी कहता है कि earlier in this section we have learned that when particles are close packed resulting in either a CCP or the HCP structure, two types of voids are generated. While the numbers of the octahedral voids present in the lattice is equal to the number of the closed packed particles, the number of the tetrahedral voids generated is twice this number. Tetrahedral voids जो होते हैं डबल हो जाते हैं. In ionic fluids, the bigger ions, usually anions, form the closed packed structure, and the small ions, usually cations, occupy the voids. If the latter ion is small enough, then the tetrahedral voids are occupied. If bigger than the octahedral voids, all octahedral voids or the tetrahedral voids are not occupied. In a given compound, the fraction of the octahedral or the tetrahedral voids that are occupied depends upon the chemical formula of the compound, as can be seen from the following examples. The question is a compound is formed by the two element fraction by atoms of the element by as anions make the CCP and those of the element X the cation occupy the octahedral voids. तो बाटी द फॉर्मूला ऑफ द कंपाउंड तो एक्स बाई हो जाएगा डायरेक्ट क्योंकि जितना CCP होता है उतना ही ऑक्टाहेड्रल voids पे जो होते हैं. नेक्स्ट क्वेश्चन है कि एटम्स ऑफ द element B forms the HCP lattice and those of the element A occupy the 2/3 of the tetrahedral voids. ठीक है. HCP में टोटल टेट्राहेड्रल voids हो जाएगा 12, तो 12 का 2/3 आ जाएगा कितना 8. तो A हो गया 8 और B कितना हो गया तो B हो गया 6. तो A8 B6 करने का मतलब A4 ठीक है आ जाएगा A4 और B3 ऐसा कुछ आना चाहिए. तो A4 B3 है जो इसका आंसर हो जाएगा. अब एनसीईआरटी आगे बोल रहा है कि लोकेटिंग द टेट्राहेड्रल एंड द ऑक्टाहेड्रल voids के लिए कहाँ पर होते हैं ये. तो वी नो डैट क्लोज पैक्ड स्ट्रक्चर है बोथ टेट्राहेड्रल एंड द ऑक्टाहेड्रल voids. लेट अस टेक द CCP और द FCP स्ट्रक्चर एंड लोकेट द voids इन इट. तो लोकेटिंग द टेट्राहेड्रल voids कहता है कि लेट अस कंसीडर यूनिट सेल ऑफ द CCP और द FCC लैटिस. द यूनिट सेल इज डिवाइडेड इनटू 8 स्मॉल क्यूब्स. Each small cube has the atoms at the alternate corner. In all, each small cube has the 4 atoms. When joined to each other, they make a regular tetrahedron. Thus, there is one tetrahedral void in each small cube and the 8 tetrahedral void in the total. Each of the 8 small cubes have one void in the one unit cell of the CCP structure. We know that CCP structure has 4 atoms per unit cell. Thus, the number of the tetrahedral voids is twice the number of the atoms. अब यहाँ पर दिया हुआ 8 tetrahedral voids per unit cell of the CCP structure और यहाँ पर 1 tetrahedral void showing the geometry. अब लोकेटिंग द octahedral voids तो octahedral voids जो होते हैं let us again consider the unit cell of the CCP or the FCC lattice. The body center of the cube C is not occupied but it is surrounded by the 6 atoms on the face center. If these face center are joined on an octahedron is formed, thus this unit cell has the one octahedral void at the body center of the cube. Besides the body center, there is one octahedral void at the center of each of the 12 edges. It is surrounded by the 6 atoms, 4 belonging to the same unit cell, 2 on the corners and 2 on the face center, and the 2 belonging to the 2 adjacent unit cell. Since each edge of the cube is shared between 4 adjacent unit cells, so it is octahedral void located on it. Only 1/4 of each void belongs to a particular unit cell. Our location of the octahedral void per unit cell of the CCP or the FCC lattice at the body center of the cube at the center of each edge only one such void is shown. तो thus in the cubic closed packed structure octahedral void at the body center of the cube हो जाएगा 1 और 12 octahedral voids 12 octahedral voids located at the each edge and shared between the 4 unit cell. तो 12 गुना 1/4 यानी कि 3 आ जाएगा. तो टोटल नंबर ऑफ octahedral voids आएंगे 4. We know that in the CCP structure each unit cell has the 4 atoms. Thus the number of the octahedral voids is equal to this number. अब अगर पैकिंग एफिशिएंसी की बात करें तो एनसीईआरटी कहता है कि इन व्हाटएवर वे द कांस्टेंट पार्टिकल्स एटम्स स्मॉल फॉर द आयंस आर पैक्ड देयर इज ऑलवेज सम फ्री स्पेस इन द फॉर्म ऑफ द voids. Packing efficiency is the percentage of the total space filled by the particles. Let us calculate the packing efficiency in the different types of the structure. तो पैकिंग एफिशिएंसी अगर हमको निकालना होगा HCP में तो HCP में जो पैकिंग एफिशिएंसी आता है वो आता है 74%. ठीक है डायरेक्टली गा सकते हैं. क्यूबिक क्लोज पैकिंग साइड्स आर नॉट प्रोवाइडेड विद द स्पेयर फॉर द सेक ऑफ द क्लैरिटी. ठीक है और उसी तरह से अगर हमको बॉडी सेंटर्ड में जो पैकिंग फ्रैक्शन आता है वो कितना आता है, तो 68%। ठीक है, डायरेक्ट यही से पूछता है, मेथड निकालने का नहीं पूछता है। सिंपल क्यूबिक यूनिट सेल में पैकिंग फ्रैक्शन कितना आता है, तो सिंपल क्यूबिक में पैकिंग फ्रैक्शन आता है 52.4%। नेक्स्ट है कैलकुलेशन इन्वॉल्विंग द यूनिट सेल डायमेंशन। तो कहता है कि फ्रॉम द यूनिट सेल डायमेंशन इट इज पॉसिबल टू कैलकुलेट द वॉल्यूम ऑफ द यूनिट सेल। Knowing the density of the metal, we can calculate the mass of the atom in the unit cell. The determination of the mass of a single atom gives an accurate method of the determination of the Avogadro constant. Suppose an edge length of a unit cell of a cubic crystal determined by the X-ray diffraction is A and D, the density of the solid substances, and M the molar mass. In the case of the cubic crystal, volume of the unit cell आता है AQ। सही है, तो डेंसिटी ऑफ द यूनिट सेल कितना आ जाएगा, डेंसिटी ऑफ द यूनिट सेल आ जाएगा, इसका फॉर्मूला हो गया जेड डी इक्वल टू जेड एम बाई ए क्यू इंटू एन ए। ठीक है, ये इसका डेंसिटी का फॉर्मूला आता है। तो कहता है कि रिमेंबर द डेंसिटी ऑफ द यूनिट सेल इज द सेम एज द डेंसिटी ऑफ द सब्सटेंस, देन द डेंसिटी ऑफ द फ्लूइड कैन ऑलवेज बी डिटरमाइंड by the other method. Out of the 5 parameters D, Z, M, A and N A, if any 4 are known, we can determine the fifth. क्लियर हो गई बात। तो क्वेश्चन है कि एन एलिमेंट है जो बॉडी सेंटर्ड बीसीसी स्ट्रक्चर विथ सेल एज ऑफ द 288 पिकोमीटर, द डेंसिटी ऑफ द एलिमेंट इज 7.2 ग्राम पर सेंटीमीटर क्यूब। तो हाउ मेनी एटम्स आर प्रेजेंट इन 208 ग्राम ऑफ द एलिमेंट। तो वॉल्यूम ऑफ द यूनिट सेल है 288 गुना 10 का पावर माइनस 12, यानी कि 2.39 गुना 10 का पावर माइनस 23 आएगा। अब वॉल्यूम ऑफ 208 ग्राम ऑफ द डेंसिटी, तो मास बाय डेंसिटी आ जाएगा 28.88 सेंटीमीटर क्यूब। तो नंबर ऑफ द यूनिट सेल इन दिस वॉल्यूम आ जाएगा 28.88 बाई 2.39 गुना 10 का पावर माइनस 23, तो 12.08 गुना 10 का पावर 23 यूनिट सेल। क्लियर हो गई बात। तो इच बीसीसी में 2 एटम होते हैं, देयरफॉर द टोटल नंबर ऑफ द एटम्स इन 208 ग्राम में आ जाएगा 2 इंटू एटम्स यूनिट सेल गुना 12.08 गुना 10 का पावर 23 यूनिट सेल, तो आ जाएगा 24.16 गुना 10 का पावर 23 एटम। अब आगे बढ़ाते हैं, तो आगे है कि एक्सरे डिफ्रैक्शन ऑफ स्टडीज शो दैट द कॉपर क्रिस्टलाइज इन एन एफईसी यूनिट सेल विद द एज of the 3.6 गुना 10 का पावर माइनस 8 सेंटीमीटर। इन ए सेपरेट एक्सपेरिमेंट कॉपर इज डिटरमाइंड टू हैव अ डेंसिटी ऑफ 8.92 ग्राम पर सेंटीमीटर क्यूब। तो कैलकुलेट द एटॉमिक मास ऑफ द कॉपर। तो कॉपर का जो डेंसिटी के अनुसार हो जाता है जेड एम बाई ए क्यू इंटू एन ए, तो इस तरह से एटॉमिक मास जो आ जाएगा, सॉरी ये अलग क्वेश्चन था, एटॉमिक मास है जो एम से निकाल सकते हैं, तो डी एन ए इंटू ए क्यू बाई जेड। तो यहाँ से जेड कितना एटम लेंगे, 4 एटम, क्योंकि कौन सा हो गया ये एफसीसी में 4 हो जाता है इफेक्टिव, तो कॉपर का आ जाए 53.1 न्यू। अगला क्वेश्चन है कि सिल्वर फॉर्म्स द सीसीपी यानी कि एफसीसी लैटिस एंड एक्सो स्टडी ऑफ क्रिस्टल फॉर दैट एज लेंथ ऑफ द क्यू इज 408.6 पिकोमीटर। देखो कि डेंसिटी ऑफ द सिल्वर, तो डेंसिटी इक्वल टू होता है जेड एम बाई ए क्यू इंटू एन ए। तो यहाँ से डी आ रहा है कितना 105.5 10.5 ग्राम पर सेंटीमीटर क्यूब। अब बात करते हैं इम्परफेक्शंस इन द सॉलिड्स की। तो कहता है कि ऑल द क्रिस्टलाइन सॉलिड्स हैव शॉर्ट रेंज एज वेल एज द लॉन्ग रेंज ऑर्डर इन द अरेंजमेंट ऑफ देयर कंस्टिट्यूएंट पार्टिकल्स, येट क्रिस्टल्स आर नॉट परफेक्ट। यूजुअली a solid consists of an aggregate of a large number of the small crystal. These small crystals have defects in them. This happens when the crystallization process occurs at a fast or the moderate rate. Single crystals are formed when the process of the crystallization occurs at extremely slow rate. Even these crystals are not free of the defects. The defects are basically irregularities in the arrangement of the constituent particles. Broadly speaking, the defects are of two types, namely the point defects and the line defects. Point defects are the irregularities or the deviation from the ideal arrangement around a point or an atom in a crystalline substance, whereas the line defects are the irregularity or the deviation from the ideal arrangement in the entire range of the lattice point. These irregularities are called the crystal defects. We shall confine our discussion to the point defects only. Type of point defects. So point defects can be classified into 3 types: stoichiometric defects, impurity defects, and the non-stoichiometric defect. Stoichiometric defect आता है कि these are the point defects that do not disturb the stoichiometry of the solid. They are also called intrinsic or thermodynamic defect. Basically, these are of 2 types: vacancy defects and the interferential defect. अगला point defect है stoichiometric defect में vacancy defect. तो vacancy defect when some of the lattice parts are vacant, the crystal is said to have vacancy defect. This results in the decrease in the density of the substance. This defect can also develop when the substance is heated. Next है interstitial defect. तो कहता है when some constituent particles, atoms or the molecules occupy an interstitial site, the crystal is said to have the interstitial defect. This defect increases the density of the substance. तो इंटरस्टिशियल डिफेक्ट here डेंसिटी को क्या करता है, इंक्रीज करता है, ये दिए हुए वैकेंसी डिफेक्ट. नेक्स्ट है कि वैकेंसी एंड द interstitial defects are, as explained above, can formed by the non-ionic fluids. Ionic fluids must always maintain the electrical neutrality rather than simple vacancy or the interstitial defects. Therefore, the defects are the Frankel and the Schottky defects. अब अगर आगे बढ़ें तो आगे है फ्रेंकल डिफेक्ट. तो कहता है कि the defect is shown by the ionic fluids. The smaller ion, usually the cation, is dislocated from its normal site to the interstitial site. It creates a vacancy defect at its original site and an interstitial defect at its new location. Frontal defect is also called the dislocation defect. It does not change the density of the fluid. Frontal defect is shown by the ionic substance in which there is a light difference in the size of the ions, for example ZnF, AgCl, AgBr and AgI, due to the small size of the Zn plus 2 and the Ag plus ion. फिर आता है Schottky defect. तो कहता है कि it is basically a vacancy defect in the ionic fluid. In order to maintain the electrical neutrality, the number of the missing cation and the anions are equal. Again, Schottky कह रहा है कि like the simple vacancy defect, Schottky defect also decreases the density of the substance. Number of such defects in the ionic fluids is quite significant. For example, in the NaCl, there are approximately 10 to the power 6 Schottky pair per centimeter cube at the room temperature. In 1 centimeter cube, there are about 10 to the power 22 ion. Thus, there is one Schottky defect per 10 to the power 15 ion. Schottky defect is shown by the ionic substances in which the cation and anion are almost similar sizes. For example, NaCl, KCl, CaCl and AgBr. It may be noted that AgBr shows both Frankel as well as the Schottky defects. Impurity defects की बात करें तो if the molten NaCl containing a little amount of the FrCl2 is crystallized, some of the parts of the Na plus ion are occupied by the Fr plus 2. Each Fr plus 2 replaces the two Na plus ion. It occupies the site of the one ion and the other site remains vacant. The cationic vacancy thus produced are equal in the number of to that of the Fr2 plus ions. Another similar example is the solid solution of the CdCl2 and the AgCl. यहाँ पर ये इंट्रोडक्शन ऑफ द कैटायन वैकेंसी इन द NaCl बाय द सब्स्टिट्यूशन ऑफ द Na प्लस बाय द Fr2 प्लस. ये दिया हुआ है फ्रेंकल डिफेक्ट्स और इधर ये दिखाया हुआ है Schottky डिफेक्ट्स. क्लियर हो गई बात. आगे आ जाते हैं तो आगे है नॉन स्टोसोमेट्रिक डिफेक्ट्स. कहता है कि द डिफेक्ट्स discussed so far do not disturb the stoichiometry of the crystalline substance. However, a large number of the non-stoichiometric inorganic solids are known which contain the constituent elements in the non-stoichiometric ratio due to the defects in their crystal structure. These defects are of two types, metal excess defect and the metal deficiency defect. Metal excess defect की बात करें तो metal excess defect due to the anionic vacancies, alkali halides like the NaCl and the KCl show this type of defect. When the crystals of NaCl are heated in the anatosphere of the sodium vapor, the sodium atoms are deposited on the surface of the crystal. The chloride ions diffuse to the surface of the crystal and combine with the Na plus atom to give the NaCl. This happens by the loss of the electron by the sodium atoms to form the Na plus ion. The lead electron diffuse into the crystal and occupy the anionic sites. As a result, the crystal now has an excess of the sodium. The anionic sites occupied by the unpaired electrons are called F center from the German word Farbengenter for the color center. They impart the yellow color to the crystal of the NaCl. The color results by the excitation of these electrons when they absorb the energy from the visual light falling on the crystal. Similarly, excess of the lithium make LiCl crystal pink and excess of potassium make the KCl crystal violet or the lilac color का. अब बात करते हैं मेटल एक्सेस डिफेक्ट ड्यू टू द प्रेजेंस ऑफ द एक्स्ट्रा कैटायन एट द इंटरस्टिशियल साइट. तो इसमें डेंसिटी है जो बढ़ जाता है. जिंक ऑक्साइड इज वाइट इन कलर एट द रूम टेम्परेचर. ऑन हीटिंग इट लूजेज ऑक्सीजन एंड टर्न्स येलो. तो ZnO को अगर हीट करते हैं तो है जो Zn प्लस 2 और हाफ O2 प्लस 2 इलेक्ट्रॉन देता है. नाउ Ncert कहता है कि नाउ देयर इज एक्सेस ऑफ द जिंक इन द क्रिस्टल एंड इट्स फार्मूला बिकम्स Zn1 प्लस XO. द एक्सेस Zn प्लस 2 ions move to the interstitial site and the electrons to the neighboring interstitial sites. Metal deficiency defect अगला है. तो there are many solids which are difficult to prepare in the stoichiometric composition and contain less amount of the metal as compared to the stoichiometric proportion. A typical example of this type of F is the FeO, which is mostly found with a composition of Fe0.95O. It may actually range from Fe0.93O to Fe0.960. In the crystal of the FeO, some Fe2 plus cations are missing and the loss of the positive charge is made up by the presence of the required number of the Fe3 plus ion. यहाँ पर दिया हुआ है एन एफ सेंटर इन ए क्रिस्टल। आगे बढ़ते हैं तो आप है इलेक्ट्रिकल प्रॉपर्टीज। तो इनसर्ट कह रहा है कि Fluids exhibit an amazing range of the electrical conductivities extending over 27 orders of the magnitude, ranging from 10 के power minus 20 to 10 के power 7 ohm per meter. Fluids can be classified into three types on the basis of their conductivities. पहला कंडक्टर, the fluids with the conductivity ranging between 10 के power 4 to 10 के power 7 ohm per meter, 10 के power 7 per ohm per meter are called the conductors. Metals of the conductivity in the order of 10 के power 7 per ohm per meter are gold conductors. Insulators, these are the fluids with very low conductivity ranging from 10 के power minus 20 to 10 के power minus 10 per ohm per meter, or semiconductor. So these are the fluids with conductivity in the intermediate range of 10 के power minus 6 to 10 के power 4 ohm per meter. Conduction of the electricity in the metals अगर देखें तो एक कंडक्टर में conduct electricity through the movement of the electrons or ions. Metallic conductors belong to the former category and the electrolytes to the latter. Metal conduct electricity in the solid as well as in the molten state. The conductivity of the metal depends upon the number of the valence electron available per atom. The atomic orbitals of the metal atom form the molecular orbitals which are so close in the energy to each other as to form a band. If this band is partially filled or it overlaps with a higher energy or unoccupied conduction band, then the electrons can flow easily under an applied electric field and the metals show the conductivity. If the gap between the fluid valence band and the next higher unoccupied band, conduction band, is large, electrons cannot jump to it, and such a substance has very small conductivity and it behaves as an insulator. आगे बात करें तो conduction of the electricity in the semiconductors में, तो in the case of the semiconductor, the gap between the valence band and the conduction band is small. Therefore, the some electrons may jump to the conduction band and some for the conductivity. Electrical conductivity of the semiconductors increases with the rise in the temperature, since more electrons can jump to the conduction band. Substances like the silicon and the germanium show this type of the behavior and are called as the intrinsic semiconductor. The conductivity of these intrinsic semiconductors is too low to be for practical use. Their conductivity increased by adding an appropriate amount of the suitable impurity. This process is called as the doping. Doping can be done with an impurity which is electron rich or the electron deficient as compared to the intrinsic semiconductor, silicon or the germanium. Such impurities introduce electronic defects in them. तो यहाँ पर दिखाया हुआ distinction among the metals, insulators and the semiconductors. In each case, an unshaded area represents a conduction band. तो ये हो गया पार्शियली फ्लैट बैंड, ओवरलैपिंग बैंड्स हो गया, ठीक है। नीचे में जो है बैलेंस बैंड है और ये कंडक्शन बैंड हो गया, ठीक है। ये कंडक्शन बैंड है और ये हो गया बैलेंस बैंड। तो फॉरबिडन जोन जो होता है लार्ज होता है इंसुलेटर केस में, और सेमीकंडक्टर केस में, मेटल के केस में तो ओवरलैपिंग कर जाता है कंडक्शन बैंड और बैलेंस बैंड। सेमीकंडक्टर केस में जो स्मॉल एनर्जी गैप होता है कंडक्शन बैंड के बीच में और बैलेंस बैंड के बीच में। अब बात करते हैं इलेक्ट्रॉन रिच इम्प्योरिटीज। तो silicon and germanium belong to the group 14 of the periodic table and have 4 valence electrons each. In their crystal, each atom forms 4 covalent bonds which is never been doped with a group 15 element like the phosphorus or the arsenic, which contains the 5 valence electron. They occupy some of the lattice sites in the silicon or the germanium crystal. 4 out of the 5 electrons are used in the formation of the 4 covalent bond with the 4 neighboring silicon atoms. The fifth electron is extra and becomes delocalized. These delocalized electrons increase the conductivity of the doped silicon or the germanium. Here the increase in the conductivity is due to the negatively charged electron, hence silicon doped with electron-rich impurity is called as the N-type semiconductor. अब अगर बात करें इलेक्ट्रॉन डिफिसिट impurity की, तो silicon or the germanium can also be doped with a group 13 element like the boron, aluminum or the gallium, which contains only 3 valence electron. The place where the fourth valence electron is missing is called the electron hole or the electron vacancy. An electron from a neighboring atom can come and fill the electron hole, but when doing so it would leave an electron hole at its original position. If it happens, it would appear as if the electron hole has moved in the direction opposite to that of the electron that filled it. Under the influence of the electric field, electrons move would move towards the positively charged plate through the electronic holes, but it would appear as if electron holes are positively charged and are moving towards the negatively charged plate. This type of the semiconductor are called as the p-type semiconductor. क्लियर होगी बात? तो यहाँ पर दिखाया गया क्रिएशन ऑफ द एन टाइप एंड द पी टाइप सेमीकंडक्टर बाय डोपिंग विद द 13 एंड द 15 एलिमेंट्स. ये हो गया परफेक्ट क्रिस्टल सिलिकॉन एटम का है. उसके बाद फिर मोबाइल इलेक्ट्रॉन्स दिखाए हुए हैं. यहाँ पर एन टाइप है तो एन टाइप में मोबाइल इलेक्ट्रॉन्स आ जाते हैं और पी टाइप में है जो पॉजिटिव होल जो आते हैं वो आ जाते हैं मेजर कैरियर्स के तौर पर. अब अगर एप्लीकेशन ऑफ एन टाइप एंड द पी टाइप सेमीकंडक्टर की बात करें तो वेरियस कॉम्बिनेशन ऑफ द एन टाइप एंड द पी टाइप सेमीकंडक्टर्स आर यूज्ड for working the electronic components. Diode is a combination of n-type and the p-type semiconductors and it is used as a rectifier. Transistors are made by sandwiching a layer of one type of the semiconductor between the two layers of the other type of the semiconductor. NPN and PNP type of the transistor are used to detect or amplify radio or the audio signals. The solar cell is an efficient photodiode used for conversion of the light energy into the electrical energy. Germanium and silicon are the group 14 elements and therefore have a characteristic balance of the 4 and they form the 4 bonds as in the diamond. A large variety of the solid state material have been prepared by a combination of the group 13 to 15 or the 12 to and 16 to stimulate average balance of the 4 as in the germanium or the silicon. Typical compounds of the group 13 to 15 are the INSB, AIP and the GAAS. Gallium arsenide GAAS semiconductors have very fast response and are revolutionized the design of the semiconductor devices. ZNF, CDF, CDFC, HDT are the examples of the group 12 to 15 compounds. In these compounds, the bonds are not perfectly covalent and the ionic character depends on the electronegativity of the two elements. It is interesting to learn that transition metal oxides show marked difference in the electrical properties. TiO, CrO2, ReO3 we have like the metals. Ruthenium oxide ReO3 is like the metallic copper in its conductivity and appearance. Certain other oxides like the Bro, BO2, BO3, TiO3 show the metallic or the insulating property depending on the temperature. अब बात करते हैं मैग्नेटिक प्रॉपर्टीज की. तो every substance has some magnetic property associated with it. The origin of each property lies in the electrons. Each electron in an atom behaves like a tiny magnet. Its magnetic moments originate from the two types of the motion: its orbital motion around the nucleus and its spin around its own axis. Electron being a charged particle and undergoing this motion can be considered as a small loop of the current which possesses a magnetic moment. Thus, each electron has a permanent spin and an orbital magnetic moment associated with it. Magnitude of this magnetic moment is very small and is measured in the unit called the Bohr magneton. It is equal to 9.27 × 10⁻24 ampere meter square. On the basis of their magnetic properties, substances can be classified into 5 categories: paramagnetic, diamagnetic, ferromagnetic, antiferromagnetic and the ferrimagnetic. तो यहाँ पर दिए हुए डेमोन्स्ट्रेशन ऑफ द मैग्नेटिक मोमेंट एसोसिएटेड विद द एन ऑर्बिटिंग इलेक्ट्रॉन एंड एन स्पिनिंग इलेक्ट्रॉन. ये यहाँ पर मैग्नेटिक मोमेंट हो गया एटॉमिक न्यूक्लियस और यहाँ पर डायरेक्शन ऑफ स्पिन दिए हुए हैं और मैग्नेटिक मोमेंट है जो दिए हुए हैं. तो एनसीईआरटी पैरामैग्नेटिज्म के लिए लिखता है कि पैरामैग्नेटिक सब्सटेंसेज आर वीकली अट्रैक्टेड बाय ए मैग्नेटिक फील्ड. दे आर मैग्नेटाइज्ड इन द मैग्नेटिक फील्ड इन द सेम डायरेक्शन. दे लूज देयर मैग्नेटिज्म इन द एब्सेंस ऑफ द मैग्नेटिक फील्ड. Paramagnetism is due to the presence of one or more unpaired electrons which are attracted by the magnetic fields. O2, CO2 plus, Fe3 plus, Cr3 plus are some example of such substances. Diamagnetism, तो कहते हैं diamagnetic substances are weakly repelled by a magnetic field. H2O, NaCl, C6H6 are some example of the such substances. They are weakly magnetized in a magnetic field in opposite direction. Diamagnetism is shown by those substances in which all the electrons are paired and there are no unpaired electrons. Pairing of the electrons cancel their magnetic moment and they lose their magnetic character. फिर आता है फेरोमैग्नेटिज्म. तो ए फ्यू सब्सटेंसेस लाइक द आयरन, cobalt, nickel, gadolinium and CrO2 are attracted very strongly by a magnetic field. Such substances are called as the ferromagnetic substances. Besides the strong attraction, these substances can be permanently magnetized. In solid state, the metal ions of the ferromagnetic substances are grouped together into small regions called as domains. Thus, each domain acts as a tiny magnet. In an unmagnetized piece of a ferromagnetic substance, the domains are randomly oriented and their magnetic moments get cancelled. When the substance is placed in magnetic field, in all the domains get oriented in the direction of the magnetic field and a strong magnetic field is produced. This ordering of the domains persists even when the magnetic field is removed and the ferromagnetic substance become a permanent magnet. Next, antiferromagnetism. तो कहता है substances like the MnO showing the antiferromagnetism have domain structure similar to the ferromagnetic substances, but the domains are oppositely oriented and cancel out each other's magnetic moment. फिर आता है फेरीमैग्नेटियम. तो कहता है कि फेरीमैग्नेटियम इज ऑब्जर्व्ड when the magnetic moments of the domains in the substance are aligned in the parallel and the anti-parallel direction in the unequal number. They are weakly attracted by the magnetic field as compared to the ferromagnetic substances. Fe3O4 magnetic and the ferrites like the Mg Fe2O4 and Zn Fe2O4 are examples of such substances. These substances also lose the ferrimagnetism on heating and become paramagnetic. तो यहाँ पर दिया सिमेट्रिक एलिमेंट ऑफ द मैग्नेटिक मोमेंट्स. ए जो है वो है फेरोमैग्नेटिक, बी जो हो गया वो है एंटी फेरोमैग्नेटिक और सी जो है वो है फेरीमैग्नेटिक. अब समरी में एनसीईआरटी कह रहा है कि solids have the definite mass, volume and the shape. This is due to the fixed position of their constituent particles, short distances and the strong interaction between them. In the amorphous solid, the arrangement of the constituent particles is only on short range order and consequently they behave like the supercooled liquids, do not have the sharp melting points and are isotropic in the nature. In the crystalline solids, there is long range order in the arrangement of their constituent particles. They have sharp melting point, are anisotropic in nature, and their particles have the characteristic shape. The property of the crystalline solid depend upon the nature in the interaction between their constituent particles. On this basis, they can be divided into four categories, namely molecular, ionic, metallic, and the covalent solids. They differ widely in their properties. The constituent particles in the crystalline solids are arranged in a regular pattern which extends throughout the crystal. This arrangement is often depicted in the form of the three-dimensional array of the points, which is called the crystal lattice. Each lattice point gives the location of one particle in a space. In all the 14 different types of the lattices are possible, which are called the Bravais lattices. Each lattice can be generated by repeating its small characteristic portion called a unit cell. A unit cell is characterized by its edge length and three angles between these edges. Unit cell can either be primitive, which have particles only at their corner position, or centered. The centered unit cell have additional particles at their body centered, at the center of the each face centered, or at the center of the two opposite faces end centered. There are 7 types of the primitive unit cell. Taking centered unit cell also into the account, there are 14 types of the unit cell in all, which results in the 14 Bravais lattices. Close packing of the particles result in two highly efficient lattices, hexagonal close packed HCP and the cubic close packed CCP. The latter is also called the face-centered FCC lattice. In both of these packings, 24% of space is filled. The remaining space is present in the form of the two types of the void, octahedral voids and the tetrahedral voids. Other types of packing are not close packing and have less efficient packing of the particles, while in the body-centered cubic lattice BCC 68% of space is filled. In the simple cubic lattice, only 52.4% of space is filled. Solids are not perfect in the structure. There are different types of the imperfection or the defects in them. Point defects and the line defects are common type of the defects. Point defects are of three types: osteosymmetric defects, impurity defects, and the non-osteosymmetric defects. Vacancy defect and the interstitial defect are the two basic types of the osteosymmetric point defects. In ionic solids, these defects are present at the Frankel and the Schottky defects. Impurity defects are caused by the presence of an impurity in the crystal. In ionic solids, when the ionic impurity has a different valence than the main compound, some vacancies are created. Non-osteosymmetric defects are of metal excess type and the metal deficient type. Sometimes calculated amounts of the impurity are introduced by doping in the semiconductor that change their electrical properties. Such materials are widely used in the electronic industry. Solids show many types of the magnetic property like the paramagnetism, diamagnetism, ferromagnetism, antiferromagnetism, and ferrimagnetism. These properties are used in audio, video, and other recording devices. All these properties can be correlated with the electronic configuration of the structures. तो यहाँ पर सॉलिड स्टेट का एनसीईआरटी है जो कंप्लीट होता है. ठीक है.